This is an example of a VAMAS file that has been created from a pair of ASCII files, and each file contains binding energy and counts per second. The binding energy is uniform in step size, and corresponding to each binding energy we have an intensity which is in counts per second, but other than these two pieces of information we have no information about the context for these data. And the context for the data is important. For example, these data were measured using a magnesium anode, and as a consequence we have a primary photoemission line, and then we have satellite photoemission lines corresponding to different resonances, albeit minor resonances, in the magnesium X-ray spectrum. So without the context of the magnesium anode we may interpret this peak as being something significant in terms of the chemistry of the sample. Data files converted by the DAT filter makes use of a set of files that are all located in the same directory with the file extension .dat. And these files are read and converted to a VAMAS file by specifying a name which can be any name .dat and then minus anode mg. So minus anode mg means that these data will be treated as if they've been collected with a magnesium anode. And when they're converted, the two columns of data that represent the binding energy and the intensity, and these are all at a uniform increment in the binding energy, are then read, and each file within that directory is entered into a new VAMAS file, resulting in a set of data that can be processed as a unit within CasaXPS. To convert a directory we use an option that is a convert to VAMAS file, and we can then select a directory that contains the set of DAT files. So to make a conversion we can say this is palladium 3d.dat, and then we can add minus anode and mg. When I press open, the directory is read, converted into a VAMAS file, and the new VAMAS file is then opened in CasaXPS. This is the new VAMAS file. So it's written back to the original directory, and each ASCII file is read and entered into a new VAMAS file. So each one of these represents the files that were in the directory. It's calculated the range for the binding energy, and this is the element transition because there's no information about what these data actually are. So having selected these, we can look at the element transition field and assign the palladium and 3D, and when I press OK, the new element transition field has been applied to these data and now represents the header for this column. So we can then see all of these displayed in CasaXPS. Since these data were collected using a magnesium anode, and we specified a magnesium anode when we converted these data, the information that's within the VAMAS block includes the fact that we do have a source which is magnesium and the photon energy for the primary resonance peak from the magnesium anode. However, there are other X-ray peaks of lesser importance, but nevertheless they are part of the spectrum that comes off the magnesium anode, and they produce photoemission with an offset and a reduced signal relative to the primary photoelectron process. So what we're going to do now is use a feature on the data editor property page that says remove satellites, and to do this we need to specify a region that defines the range of a photoelectron pair, in this case the palladium 3D, and when we press create and just adjust so that we can specify the pair of peaks that were primary peaks, and then go to the data editor and press the remove satellite button, and this processes the data and produces a background that has the satellites removed. Remove satellites removes the satellites from the process data only. The raw data is still in the original state, so we're able to undo these operations using the undo button on the spectrum processing dialog window. So we have the satellites returned here. The dataset contains not just one spectrum, but it has a set of spectra, all of which contain satellite information that we would like to process out of these data. So if we go to the regions property page, and then we'll just adjust the region so it spans all of these spectra and propagate. So the region's now propagated to each of these spectra. Then back to the data editor property page, there's an option here that says satellite subtract all, and this will perform satellite subtraction based on regions defined on each one of these spectra that are overlaid in the active tile. So when I press this button, I get a dialog window that says, do you want to subtract the satellites from the 26 spectra in the active tile? That's referring to these spectra here, and we have the choice of either doing the subtraction on the raw data, so we can't undo it anymore, or we can use no, which will indicate that the processing will occur and the raw data will remain the same. So I will use that option, and you can see now that we have a set of spectra and the satellites have all been subtracted. So if I wish to retain this satellite subtraction, I can perform the process again, and this time I'll say yes. And since I've now processed the raw data, I'm going to save these data to a new file name. And rather than calling it raw, I'll call this processed. And the reason that I've saved this to a new file name is because when I use the processing history, I'm not able to undo these data anymore. That is because the raw data has had the satellites removed, and hence I've saved to a new file name.